Today's lecture is about vector fields, but first, let's understand the basic concept of fields right here. As you can see, fields are functions. So we have the keyword right at the get-go, functions. So fields are functions, but not just any functions. They have to be the ones that give values at each point in the space. Well, what does it mean to give a value to a point in the space? Let's take a look at this explanation right here. For example, you have this location xy in the space, alright? This coordinate. When you see a coordinate like this, just x and y, you know right away that we are working in two-dimensional space. And at this particular location, I want to assign a value to it. And I'm going to use this function value for that right here. So what you see right here is a regular multi-variable functions with two inputs, x and y, right? And we also have one output, which is the function value. Today, I want you to look at this f of xy differently. No more input and output. We are going to look at this as a value assigned to each point in the space. So think of a map and then you put values at each point, alright? Now, let's make a note right here. This is going to be viewed as value assigned to each point at each point xy, and in this case this is going to be in two-dimensional space. So it's the way that we look at this f of xy differently that makes them field. Alright, and now we are going to extend this concept to three-dimensional space. Instead of having a coordinate of xy, we are going to have xyz instead. xyz as location in space, and then we assign a value to that location and we use the function value again. And once again, this is going to mean value at each location, each coordinate xyz, and this time it's going to be 3D. Alright, so what you are looking at here is the concept of fields. Alright, so in the end, fields are functions, and make a note right here, they are multi-variable functions. Multi-variable function. It's just the way that we look at them differently that makes them field. Alright, so there you go, the concept of fields. Now, let's take a look at this f of xy and f of xyz that we just put in there. Let's take a look at the value that we assign to them. We assign this f value, and you can see that they are scalars. So make a note right here that we just assigned scalars to each location. So we just did this scalars. Oh, I'm sorry, it's supposed to be scalars. Which means that the values that we assign to them, they all have to be scalars. Scalar right here and also scalar right here. When you assign a scalar to each location in the space, and when you look at this as a field, we call them scalar field. Alright, and that is the concept of scalar field. You assign a scalar value to each location. Alright, now it turns out that we don't have to assign a scalar to each location. We can assign a vector to each location as well. So let's take a look here. At each location x, y, instead of using a scalar and assign it to them, we can assign a vector to that location. And I'm going to call that r. And same with three-dimensional space x, y, z. We are going to assign a vector as well. Now this, let's put a meaning to it. It's going to be a vector that is assigned to each location in the space at each xy in 2D. How is that going to be, right? Vector at each location in the space. So let's take a look at this example on the right hand side so you can see how it's going to look like. So what you see right here on the right hand side, this is vector field. Vector field in two-dimensional space. So we are looking at x-axis right here and y-axis right here, and at each location in the space we have different vectors, as you can see here. I hope you can see them. At each location all of these points have different vectors. And that is an example of vector fields in 2D, how it looks like. You sort of see the flow in there, right? Now, we can do the same for the three-dimensional space. So for this XYZ, it's going to be vector again. Vector at each location, at each XYZ in 3D. And we can take a look at this illustration on the right hand side. What you see right here is a vector field in 3D. Vector field in 3D, which means that at each location in the space, in three-dimensional space, we are going to have different vectors. Alright, keep in mind that all these vectors can have different directions and different sizes. Alright, they don't have to look the same at each point. Okay, so that is the idea of vector fields. It means that we assign vector to each point in the space. Alright, now let's take a look at the expression of the vector field, how it's going to look like in terms of components. So we are going to write this again, R of xy. So this is going to be the vector that we put into each location. And of course, it's a vector. It must have the components. And we are working in 2D, right? So it's going to have I and j component. And for each component of them, they have to be different at each point, and it's going to be assigned based on the location. The I component is going to assign, the value for it is going to depend on x and y. And we use function of x and y to explain this I component. And for j component, same thing, depends on x and y. But it doesn't have to be the same as the I component, so we use g. Alright, so each component can change differently. So what you see right here is the expression of the vector field in terms of components, and this one is for two-dimensional space. Alright, and of course I need to write another one for the 3D, and it's going to be vector field for 3D right here, x, y, and z, and this time we have three components. So first one, same thing. It has to depend on x, y, and z for the first component. Alright, and then g of x, y, and z for the j component, and for the last component, let's use h for that, x, y, and z for k component. And this is the expression of the vector field in terms of components for 3D. Alright, notice that the components depend on the location of x, y in 2D and depends on the location x, y, z in 3D. What you are looking at here is a multi-variable vector functions. Multi-variable functions. Why is that so? Multi-variable means that you have multiple inputs. As you can see here, you have multiple inputs. 3 of them here and 2 of them here. Oh, I'm sorry, it's supposed to be vector functions. So change this to vector function. Alright, so when it comes to multi-variable, we are talking about input. And what about vector right here? Is the output. That is a vector. And as you can see here, the output of this function is a vector, and that's why this is vector functions. Alright, not too bad, right? That is the concept of field, scalar field, and vector field. It's all about assigning something in the space. That's all. That's fields. Now, let's move to the next slide, and this is going to be about a new operator to you. So today I'm going to introduce to you a new operator, and that operator is called del. The shape of this operator is the upside down triangle. So this is called del. And we are going to use this del multiple times and in multiple applications, and you are going to use this in your later years as well. So let's take a look at this del and what kind of operations that we can use this on. So we can use this on gradient. This is the first one. We can use del on to find the gradient. So make a note right here. This first one is the gradient. Oh, let's put it down here. Gradient right here. Right, gradient. Sometimes we just call it grad. Okay, so this is gradient of f. And then we can use this del to find divergence of a vector field. Divergence. Alright, sometimes we call that for short diff. And we can use this same del for curl. Alright, that is the third one, and the last one is Laplacian. Okay, this one is Laplacian. So we have 4 operations right now, but in this course and for the midterm, we are going to focus on this gradient only. Alright, now before I talk about this gradient, I want to point something out to you. What you see right here for the gradient, we perform this del on a regular f. What you see right here is a regular f, which means that this is a scalar field. Scalar field. Or you can view it as a function, scalar function. Alright? But when you try to find the divergence by using del, we perform it on big F right here. This is a vector field. So when it comes to divergence, it has to be applied on vector field. Okay, vector field. Or function if you want. And let's take a look at curl. Curl, once again, is applied on big F, so it has to be vector field. You don't apply curl on a scalar field. Same for divergence. Alright, and for the Laplacian, we are back to this regular F, and it's going to be scalar field. Just make a note right here. When it comes to gradient, you apply it on scalar field. When it comes to divergence and curl, you applied it on vector fields. And Laplacian, once again, scalar field. And back to this gradient, which is the focus for this course and the midterm. Let's take a look at the formula for this gradient. So if you have this f function, okay, let me put it this way. So you have this function, multi-variable function, f of xy, and you can also view this as a scalar field. Right, scalar field in 2D. And you want to find the gradient of this, you can use this formula right away. Gradient of f, alright, I don't like this color. So let me put black right here. Gradient of this f of xy is going to be equal to this partial diff of f with respect to x, and that is the first component, I, plus partial diff of f with respect to y, and that is j component. So let's make a box around this. We only have one formula for this gradient of f. Very easy to remember. But one thing I need to remind you is that we apply this gradient to a scalar field. This one is scalar, but as a result of this operation, we have a vector. Alright? So keep in mind that when you find the gradient of a function, you have to get a vector out of that. If you get a scalar out of that, something is not right. Okay? Now, that is for 2D version. Of course, we are going to have another version for three-dimensional space where we have x, y, and z, f of x, y, and z. So what we have right here is going to be scalar field in 3D. And as you might have guessed, the formula is going to be quite similar. And it's going to be this del of f, this time x, y, and z. And we are going to have this df by dx for the first component, and df by dy for the second component, and for the last component, of course, df by dz, k component. Alright. Okay, so that is for 3D, and this one is 2D. Once again, we have f as a scalar. scalar function, scalar field, but in the end we have this vector. So let's make a note right here. Del f is always is called gradient vector. Right, del f is gradient vector. And the keyword is right here. It has to be vector. Now that we know about these formulas, we are ready to work on some examples. All right? So let's move to this slide right here. Now, there are some nice and useful properties when it comes to these gradient vectors, and that's why we use them quite a lot in engineering. So let's take a look at these properties that we have right here. Let's take a look at this number one. Gradient vectors can tell us the direction that make the function value increase the most. Alright, it seems like we have a lot of keywords going on right now, so let's go through them one by one. So this is going to be about the direction, okay, that make the function value f increase the most, right? Make f increase the most. What this means is that if you want to increase your f or function value the most or in the fastest way, all you need to do is to follow the direction of the gradient vector. So you have to follow the direction of the gradient vector in order to increase your function value the fastest. Alright, this is the first useful information you can extract out of this gradient of f. Right, now let's take a look at this number two, the second property. Here, gradient vectors can also tell us how fast the function value increases. So this time around, it's about how fast. Or in other words, it's about the rate of change when the increase occurs. So not just about the direction that we need to follow, we get to know how it's going to happen, whether it's going to be fast or it's going to be slow. Right, so two information, direction and how fast. Now, the question is, how do we extract these two informations out of this gradient vector of f? And I'm going to give you two expressions in order to find these two values. So let's start with this direction right here. This one is going to be for direction, and it's going to be this gradient of f divided by its own size, absolute value of gradient of f. The reason that I need to divide this gradient of f by its own size is because I want a unit vector. So make a note right here, this is a unit vector. Unit vector. And the reason that I want a unit vector because we are looking for a direction. When it comes to direction, we usually use a unit vector for that. So make a note right here, direction supposed to be unit vector. Because we don't want extra number into the calculation, we just want the direction. We want the size to be just 1. Alright, so make a box around this. This is going to be the direction that increase your f the fastest way. So make a note right here, this is going to be the direction that function value increases the most. Increases the most. And the key is right here. It's going to increase the fastest. Now, what about the rate? We can find that from the absolute value of the gradient vector. So we can find how fast from this absolute value of gradient vector f. And that is it. Put a box around it. That is the second information. And that is supposed to be the max rate of change of function. In other words, it's going to tell us how fast the change is going to happen. So property number one is right here, property number two right here. So we can find the direction, we can find the rate. Now that we understand how to find them, let's apply them to some examples. Let's take a look at this example number one. In this example, we see a function of two inputs, but this function can also be viewed or interpreted as a scalar field. We are working with this f right here, so it's a scalar, and we are looking at coordinates of x and y. So let's make a note right here that this function can be viewed as a scalar field in two dimensions. Scalar field in 2D. As you can see, at each location, at each coordinate of x and y, we are going to assign this scalar value to them at all the locations. So we have this scalar field to work with, and then they ask for this gradient of f, all right? Gradient of f at 3 points, 1, 0, minus 2, 0, and minus 1, minus 1. When it comes to the calculation of the gradient, it's kind of easy, so let's take a look here. All we need to do is to follow the formula. So we only have one formula for two-dimension gradient, and it's going to be this. Gradient of f of xy is going to be equal to df by dx, and that is I component, and plus df by dy, and that's for j component. That's all we need. One formula to find this gradient. Okay? Looks easy, right? So let's start by looking at this df by dx. So let's start by finding this df by dx. So we are going to diff this function right here, these terms with respect to x only. Alright? So we are going to treat y as a constant. So let's start with this term. Diff this with respect to x, of course we get 2x. Now, diff this with respect to x, we treat y as a constant, so diff this constant, we are going to get 0 out of that. And when we diff this with respect to x, this is a constant, so it becomes 0. So in the end, we have this df by dx equal to 2x. Now let's try to find this df by dy. Alright, let's try to diff this f with respect to y only. Okay, so let's take a look here. We are going to diff this with respect to y. It's going to go to 0 because x is a constant here. Diff this with respect to y, I get 2y equal to 2y, and diff this with respect to y, this 4 right here, of course it's going to go to 0. So there you go, we have this 2x and 2y for the first order partial derivative, and we can plug them back into the formula. And here we have this df, gradient of f, oh I'm sorry, not df, del f, xy equal to df by dx, that's 2x, and that's the first component, plus second component 2y, j. And there you go, we have these gradient vectors. So make a note right here, gradient vector. And it can be used for any x and y out there. So if you want to find it at 1, 0, you just plug them in. At this point, just plug them in, and same with the last one. So let's make a box around this for the complete one. This one includes the function that we have in this example. Alright, now let's find the first gradient at 1, 0. So gradient at 1, 0, let's change the color to black. F at 1 and 0. So it's going to be, I plug this one in, I get 2i. 0 goes into y right here, it's going to go away. So there you go, I got the first one. Easy, right? Next one, gradient vector at -2 and 0. So this time x equal to -2, I plug it in, I get this -4i. Alright, y equal to 0, I put it in, I get this 0j for the second component. So in the end, I have this -4i for the second gradient they asked for. Now for the last one, supposed to be this gradient of f at -1 and -1. Alright, x equal to -1 and y equal to -1. I put these two values in. I get this -2i, -2j. And there you go. We got all three gradients that we are supposed to find in this example. As you can see here, when it comes to the calculations of gradient vectors, they are quite simple and straightforward. It took little time for us to find all these three, right? Because all we need to do is to follow this one formula right here. And inside this formula, it's quite simple as well. All we need to do is to find the partial derivatives with respect to each variable. And there you go, we got all these three. Alright, the next thing we are going to do is to check these vectors that we just found, these three, whether they point to the same direction that increase the function value the most. We are going to check whether they have the properties that we mentioned earlier about the direction, about the rate of change, all right? And it's going to be about the increasing the function value. So the best way to do that is to check the function value in the space. So let's take a look at this graph right here. We are going to check the function value in the space at each coordinate x and y. So at each x and y right here, you see this function value. All right, function value at each point in the space. From the observation, the first thing we notice from this surface in the space is that the lowest point is right here, and it's right at the origin. You can compare that to the expression of the function right here. Right here, if you put 0 and 0 into x and y, you get the smallest value out of this function. So let's write down the observation down here. So from observation, okay, observation number 1 is that function value is lowest at the origin. fxy is lowest at origin, 0 and 0. And the next thing we notice from this surface is that as you move away from the origin, the function value starts to curve up, which means that the function value starts to increase as you move away from the origin. No matter how you do it, like no matter the direction you take, as you move away from the origin, like this, function value starts to climb up. Same with this direction, and same with this direction. All right, so that is the second observation. Number 2, function value increases as moved from the origin. Okay, so you know, once you go away from the origin, the function value is going to rise up. Now, the next thing we are going to do is to draw the level curves of this surface. All right, so in order to find these level curves, we are supposed to set the function value at different values of k. All right, so we are going to do this right here. We are going to set the function value fxy to be equal to k. And we are going to assign different values of k in order to get different level curves. So let's work a little bit further with this. It's going to be x squared plus y squared, all right, minus 4 equal to k. Right, and we are going to work with this equation right here. And let's start with this k equal to 0. All right. With this k equal to 0, and you can see in this equation that in the end we are going to end up with this equation x squared plus y squared equal to 4. And this corresponds to a circle with a radius of 2. So let's draw that on the graph right here. Okay, so this is y-axis and x-axis right here, x and y. And now we are supposed to have this circle of radius 2. Okay, this is a bad scale. Let me fix that. Okay, this may be better. Okay. All right, the first one, a circle of radius 2. Okay, something like that. Not perfect circle, but we have to use this one. All right, k equal to 0 right here, and we have this circle of radius 2. Now let's try a different k equal to minus 3. And in this case, we are going to have this equation instead, x squared plus y squared equal to 1. And that is a circle of radius 1. So let's draw that circle of radius 1 right here. And this happens when k equal to minus 3. Okay, now one more. K equal to 5, all right? And we have this x squared plus y squared. Now we have 5 for k, so we have this 9 on the right-hand side of this equation. And we are looking at an equation of a circle of radius 3. So we have one more right here. Okay, circle of radius 3. Okay, so let's make a note right here. This is k equal to 5. All right. One thing I want you to notice is that k represents the function value. Let's take a look here. K represents the function value, which means that on each level curve, the function value is constant, right? So, as you can see here, the first one, k equal to minus 3. So on this level curve, the function value is constant. So make a note right here, function value, fxy, constant on each level curve. All right, and let's move to the next one. For this k equal to 0, the function value is constant all the way through on this circle. They are all equal to 0. And when you moved away to this k equal to 5, function value becomes 5 and it's constant all the way through in this circle. So you can start at this 0, at this origin right here. And as you move away, just this comes from the observation, right? As you move away from the origin, k starts to increase as long as it points away from this 0, 0. So this seems to be right. Function value increases as moved away from the origin. And the question is, which direction increases the most? And now we are back to this. Which direction increases the function value the most? And of course, in this form, it has to be moved away radially, right? In terms of radius, right? So last observation, number 3, fxy increases the most when moved. So this is the keyword, radially, from the origin. You have to move away and you have to move in the direction of the radius. All right, so that is coming from the observation. So let's take a look at this first point, 1, 0. Okay, so let's take a look at this 1, 0 right here. And what kind of vector do we have from the calculation? We have this 2i. So it's going to be a vector of length 2 points in the direction of positive x. So it's going to point in this direction. Why don't I use this red right here? It's going to point in this positive direction of x, and the length is 2. So there you go. We have this one is a gradient vector, and it points in the direction that increase the function value the most, going out radially. All right, so this seems to be true. Now let's take a look at the next one, at minus 2 and 0. Okay, minus 2 and 0. For this one, let's draw this vector right here, minus 2 and 0 right here. And the vector that we have is minus 4i. So it's going to be a vector that has a length of 4, and it points in the negative direction of x. And it's going to be this one. It's going to go out like that. And as you can see, it points in the direction that increased the function the most, going out radially. So let's assume that this one has the length of 4. The question is why it has different length. All right. As you can see from the surface right here in the graph, as you move away from the origin, the curve of this surface starts to ramp up to increase more rapidly. At this point, it's going to go up faster. So it's going to go like this, much faster than around here when you are close to the origin, which means that as you are away from the origin, you are going to increase your function value much faster, and that's why you get this longer gradient vector at minus 2 and 0, because you are further away than the first point at 1 and 0. Okay, so there you go. Not just about the direction, and the length matter too. The shorter length indicates that the increase is not that fast. But if the length is long, then the increase is going to be much larger. Now let's take a look at the last one. Right here, -1 and -1. Of course, we expect it to point away from the origin radially. So at -1 and -1 is supposed to be right here. Alright, and what kind of vector we have? -2i and -2j. So it's going to be this vector points out with the length of 2 square root of 2. Something like this. Alright. So that is -2i and -2j vector. So the vectors that we got, the gradient vectors, they correspond to the properties that we talked about earlier. So that's good news. Alright, let's move to the next two examples where we have to find the gradient vectors of some functions right here. So let's take a look at example number 2 first, this one. In this example, we have a function of two inputs, x and y, as input variables. And as you know, this same function can be viewed as the scalar field in 2 dimensions. So make a note right here, this can be viewed as scalar field in 2D, which means that at each location, x, y, or each coordinate, we assign the function value to those locations. Okay, now let's try to find out what we need to calculate here. We are supposed to find the gradient vector of f at this location, coordinate 1 and 2. So why don't we start with the gradient of f? So once again, when it comes to the calculation of the gradient vector, it's straightforward. We just need to follow the formula. Gradient of f with two inputs, x and y, is going to be equal to partial diff of f with respect to x for the first component, and then partial diff of f with respect to y for the second component. That's all we need for this example. Alright, and this is the starting point. Now let's work on this one, df by dx. So I need to find the first order partial diff of f with respect to x. Now I take a look at this function and I need to diff this function with respect to x. And as you can see here, we have this x at the denominator of this fraction, which means that we cannot diff this regularly. We are supposed to apply some trick to this one. And for me, I am going to display this fraction as this term instead, x squared plus y squared to the power of -1. Instead of looking at this as a fraction, I want to look at this as a term with some power, so that I can apply the power rule to this one. As you know, when I diff this, I can apply the power rule. The power of -1 comes down. Alright, so I have this -1 comes down, and then the power of these whole terms is going to decrease by 1. It's going to become -2, so in the end we have this x squared plus y squared. Square again at the end. Okay, and that is the power rule. But then after the power rule, we are supposed to apply the chain rule to the inside of this term. So first I need to diff this with respect to x, and of course I get 2x out of that from chain rule. So you can make a note right here that this 2x comes from chain. And then I need to diff this y squared with respect to x, but this time around I diff with respect to x only. I treat y as a constant, so y squared is going to go to 0 when you diff it. So there you go, we have this first term right there. Now what about df by dy? Let's find out about this. First partial diff with respect to y. Okay, I need to write this again, it's getting messy. So once again I see this location of y at the denominator of this fraction. So I'm going to use the same trick. Instead of looking at the fraction, I want to look at this as some terms with the power of -1. And I apply the power rule to this one. I diff this, -1 comes down, and then the power of this whole term decreases by 1. It becomes -2, so I can display that with this x squared plus y squared to the power of 2. And then I apply the chain rule, diff inside. With this one with respect to y, it goes to 0 because x is considered constant in this case. and then I diff this with respect to y, I get 2y from chain rule. Once again, make a note right here, this is chain. Now that we have found df by dx and df by dy, we can just plug them back into the formula to get this gradient vector of f for this example for any x and y. And it's going to be equal to df by dx, and that is equal to minus 2x divided by x squared plus y squared and square again at the end for the first component, right? And now for the next component, df by dy, so it's going to be minus 2y divided by same term, x squared plus y squared to the power of 2, j. There you go. We have this gradient vector for this example. Now we need to find this gradient vector at 1, 2. So all we need to do is to apply this x equal to 1 and y equal to 2 to this expression. So we can get this gradient vector of f at 1 and 2. It's going to be this. Okay, 1 goes in, I have this minus 2, alright, and then 1 square plus 2 square, and then we have square at the end, I, minus 2, y equal to 2 this time, so this divided by the same term, 1 square plus 2 square, and square at the end, j. Okay, let's work this out, and it's going to come out to be, let's change the color, minus 2 divided by 1 plus 4 becomes 5, and 5 squared becomes 25, I. Minus, alright, 2 right here becomes 4, and divided by same term, 25j. Okay, so there you go. We got this gradient vector at this particular location of 1 and 2. And the result is this right here. Let me put a box around this so it doesn't get confusing. And there you go. We get this final answer for example number 2. Now let's take a look at this example number 3 right here. In this case, we have a function again, but it's a little bit different because we have 3 input variables, x, y, and z. Okay, and as you know, a function like this can be viewed as a scalar field, and this time around it's going to be scalar field in 3D. In 3D, which means that at each coordinate x, y, z in the space, we are going to apply or assign this function value to them. Alright, now we need to find this gradient vector f at this location 1, 2, and 3. Once again, gradient vector, same formula. Gradient vector this time, it has 3 inputs, x, y, and z. So the formula is going to be a little bit different. Instead of having 2 components, we are going to have 3 components. So df by dx for the first component, I, plus df by dy for the second component, j, and last one, df by dz for the k component. Alright, so we add one more term to the formula, and once again, all we need to do is to follow this one formula. Why don't we start with this df by dx? Alright, so we are supposed to find this df partial diff of f with respect to x, right here. df with respect to x, so we need to diff this with respect to x only, right? And now let's take a look at the locations of x in this function. And as you can see here, we have 2 locations of x, one at the numerator right here, and another one at the denominator, which means that we are supposed to apply the quotient rule to this, because we have a term right here with x in it, and we also have a term right here with x in it. So we have a quotient of two terms with x. So this is u divided by v, and we want to diff this, we need to apply the quotient rule, and it's going to be v du. So v right here is going to be x plus z. Du we need to diff this u right here with respect to x, and I diff this one, I get just 1 out of that. Okay, minus u x plus y dv. I need to diff this with respect to x, and I get 1 again. Okay, so divided by this v squared, x plus z squared. So let's combine all these terms. So x right here minus x goes away, so in the end we have this z minus y divided by x plus z squared for df by dx. Now let's take a look at this df by dy. df by dy, right? Partial diff of this same function with respect to y this time. And since this got messy, I need to erase them. And let's try to diff this with respect to y. And as you can see here, we have only one y in this fraction at the numerator. So differentiating this should be easier. But before I diff this, I am going to split this fraction into 2 terms. So this can be viewed as equal to, right, x divided by this denominator of x plus z plus y divided by x plus z. So I decided to separate the numerator into 2 terms. So first of all, I need to diff this with respect to y. Of course, I get 0 out of that because everything else besides y is going to get considered as constant. Goes to 0 when you diff this with respect to y. Now I need to diff this one with respect to y, and as you can see here, y is going to go to 1. Diff this y, it becomes 1. And then I get to keep the constant down here, x plus z. You diff this y over x plus z, you get the constant out of that. Alright, and that is df by dy. Now, df by dz for the last one. And I need to erase this again. And we are supposed to diff this with respect to z. And as you can see here, we have this 1z at the denominator of this fraction. So we are supposed to apply some trick to make this easier to differentiate. So instead of looking at this as a fraction, I am going to look at this as 2 terms multiplied together, these 2 terms. So let's make a note right here. It's going to be equal to x plus y times x plus z to the power of minus 1. In this form, I can just apply the power rule to this one when I differentiate. So in the end, when I diff this, I just apply power rule. Minus 1 comes down, alright, and I get to keep the constant at the front, alright. This becomes constant in this case, so I have this x plus y, and then x plus z, the power of this term has to decrease by 1. It's going to become minus 2, so in the end, I have this x plus z to the power of 2 right here. Okay, now let's use them all in the formula. So now we got df by dx, df by dy, and df by dz. So everything comes down to right here. Gradient vector of f equal to df by dx, and that is equal to z minus y divided by x plus z squared. That's the first component. Alright, for the second component, we have this 1 over x plus z, j. Last component, df by dz, we have this, okay, minus, so I can just use right here, minus x plus y divided by x plus z squared, k component. Okay, now all we need to do is to plug these 1, 2, 3 in. X equal to 1, y equal to 2, and z equal to 3. So let's find out this gradient of f at this particular point, 1, 2, 3, equal to, okay, z minus y, so it's going to be 3 minus 2, and I get this 1. Alright, and now x plus z, 1 plus 3 squared. It's going to be All right, 1 plus 3 becomes 4, square becomes 16i. Plus 1 over x plus z. X, y, and z right here. 1 plus 3, we get 4j. 1 over 4j. Minus x plus y, 1 plus 2, we have this 3, divided by x plus z, that is 4, square becomes 16. And there you go. You have this answer for this example number 3 equal to 1 over 16i, 1 over 4j. Alright, so let's make a box around that for this final answer for this example. And the last component is minus 3 over 16k. Alright, that's it. In the end, it's just these formulas that we have to perform the calculation on. Alright, now let's move to the next slide. This one is the properties of the gradient operations. So make a note right here, this is about gradient operation. And I want you to keep in mind that gradient operation is based on the differentiation. Based on differentiation. As you know, we need to find df by dx, df by dy. Of course, in the end, it's about differentiation, which means that the properties of gradient operation is going to be similar to the properties of differentiation. And as you can see here, if you want to find, let's take a look at the sum rule. If you want to find the gradient of the sum of two functions, all you need to do, not all you need to do, you can apply, you can distribute the gradient to each one of them. Alright, and then perform the plus at the end of the calculation. You can do that, and that is the same as the differentiation. You can diff the first function, and then diff the second function, and then sum them together. Same with the subtract or the difference. Right here, if you want to find the gradient of the subtraction of two functions, you can distribute the gradient operation to each one of them separately, and then perform the minus in the end. As for constant, same thing. If you have a constant in front of a function and you want to perform the gradient operation on, you can just take the constant to the front right here. Doesn't matter. Now, for product rule, it's going to be similar to the product rule of the differentiation, which is u dv plus v du. In this case, we want to find the gradient of the product of two functions. So you are supposed to find the front gradient of back plus back gradient of front, just like this. Front diff back plus back diff front. Same logic right here. And this applies to the quotient rule as well. Instead of having this v du, in the differentiation we have this v du minus u dv divided by v squared, right? In this time, it's going to be quite similar. We want to find the gradient of the quotient of two functions, f and g. So it's going to be g gradient of f, all right? G gradient of f minus f gradient of g divided by g squared, similar to the quotient rule of the differentiation. Now, at the end, I want to add some extra properties of the gradient operations. So first of all, keep in mind that when you see this gradient of f divided by its own size, this one, if you can recall, this is going to be the direction. The direction. When you see this word direction, you need to know that it's about a unit vector. All right? That function value increases the fastest. Increase fastest. All right, this is something that we have seen before, but let's take a look at this one. Number 2, if we add a minus sign in front of that, same thing, gradient of f divided by its own size, and we have this minus sign. this turns out to be the direction that make the function value decreases the most. Right? So make a note right here. Once again, it's going to be a direction, but this time around it's going to the opposite way, right? Opposite of number 1, which means that this is going to be the direction that function value decreases the most. Fastest, same thing. So the keyword is right here. The first one is about increasing. The number 2 is about decreasing. So if you want to find the direction to follow to decrease your function value, you need to follow number 2.